Yeah, good morning to all.
Good morning.
Good morning, sir.
Yeah, good morning. So, are the slides visible?
Yes, sir.
Okay, very good. So today, let me start the shear strength of the soil, so which is one of the very fundamental. So let me talk all the basics and advanced thing about the triaxial testing and shear strength of the soil. So before take up this chapter, so if you have any questions regarding the clay mineralogy, I'm ready to answer. So does anybody require clarification on the clay mineralogy?
Sir,
Yeah,
so there was a statement in a book. If we have two soils,
yeah,
and if their liquid limit is same,
yeah.
then higher the plasticity index, dry strength will be higher.
Higher the plasticity index,
Higher will be the dry strength.
Higher the plasticity index, higher the dry strength.
And
Correct.
there was also a statement that if plasticity index is same, then higher the liquid limit, the dry strength will be less.
Both statements are true. So see, for example, this in essence, when you say now as per this statement, the liquid limit is remains same.
Yes, sir.
When the liquid limit is remains same, if the plasticity index has to increase, then which parameter has to decrease?
Plastic limit.
So what does that mean?
Earlier, the plasticity stage will be achieved earlier.
Yeah. So this is the reason. So, but this should be reversed, na? The
Yeah,
plasticity index is I means the strength should be no, correct. Plasticity high means at lesser water content it is becoming the plastic soil.
yes, sir.
So obviously, na? So lesser water content means so up to that point it can exhibit the higher strength. But as such, there is no relevance between the strength versus plasticity index. So this is an observation, but I don't think so in this as any kind of an what do you call?
Logical thing is not there, only empirical
Yeah, this is some
observation.
kind of an interpretation. So it doesn't make any, it doesn't have any logical reason.
Okay, sir.
Okay.
Okay, sir.
May I please know what is that book?
Sir, it was in Khanna and Justo.
Acha, acha. No, but I will suggest you to read other books. There was a very good book by Lambe and Whitman, or you can read Holz and Kovac, or B.M. Das.
Okay, sir.
Okay, or Applied Soil Mechanics by Gopal Ranjan.
Okay, sir. Okay.
Okay, so these are the people who really did work on the soil mechanics.
Okay, sir.
Okay, like for example, if you read Lambe and Whitman,
Yes,
so Lambe is the one person who did a lot of work on permeability, seepage, in this plastic limit,
sir.
and
Okay.
Casagrande is the person, so who is the inventor of this all the Atterberg limits.
Okay, sir.
Okay, so this Khanna and Justo, they have read all the books and they converted the understanding of the original books into Indian understanding.
Okay, sir.
Okay,
Yes, sir.
so yeah, so don't go by all these statements because it doesn't have any logical interpretation, as you rightly said.
Okay, sir.
Good. So any other question? It's a good one. But there are other things that you need to understand. There are like a liquidity index, there are like a consistency index, there are like a shrinkage index. They have some practical significance. Okay, because these when these limits are related with the natural water content, then that is called as an index. For example, when you talk about plastic limit, shrinkage limit, and liquid limit, so this indicates the state at which the soil changes from, say, hard to moldable or moldable to plastic, plastic to slurry. So these are the interpretation that can be made from the consistency. But if you look at any natural soil, there exists some natural water content. if you try to correlate these three limits with the natural water content, so then you come up with another indexes. Those are called as a consistency index, liquidity index, and shrinkage index. So if you look at any of these indices, then they have a strong relationship with the natural moisture content. So there is a belief that the natural water content should not exceed liquid limit or something, but anyhow that is practically possible. And there is also something, it should not be below the shrinkage limit or something. So they have some kind of relevance. So there is a practical relevance between the natural water content and these limits. It should not exceed certain value. And in some soils, you may often see somebody reports shrinkage limit higher than the plastic limit. So this doesn't make any sense. If you look at the graph carefully, so the shrinkage should be lower than the plastic limit. But if you do not understand properly, whatever the value you get, you simply report it. So I have seen several people reporting shrinkage limit higher than the plastic limit. Okay, so don't do such mistakes.
Okay, sir.
Okay, so any other question? Beautiful. Okay, so let me start the today's lecture, so that I will try to give you a small glimpse about the shear strength of the soil. Let us try to understand what is the fundamental meaning of strength of the soil. When you talk about strength of any material, there are primarily three kinds of the strength normally which we have dealt with. So in your undergraduation program, when you dealt with the steel, you asked to determine the tensile strength of a soil. And when you are dealing with the concrete, you were asked to determine the compressive strength of a soil. But when you are asked to deal with the soil, so you are asked to determine the shear strength. Can anybody able to explain why in case of the steel and concrete, we were not able to determine the shear strength? Why should we go for only the shear strength in case of the soil, but not for the steel and concrete? Any logical explanation from anybody?
Sir, because of their high stiffness.
Because of their high stiffness. Okay, very good. Any other reason? Any other reason by anybody? What is the field existence of the steel, concrete, and soil? How do we put them in the field, steel? And how they fail?
Steel is used inside as a member.
Yeah.
In a particular shape.
So what it does when it is embedded in a concrete? So primarily we use the steel as a reinforcement in concrete to resist the tensile stresses which are developing, because concrete is weak in tension. So in order to improve the tensile capacity of the concrete material, so we reinforce it using a steel material. So therefore the governing criterion for steel is the tensile strength, which ultimately it has to fail. Okay, so this is simple logic I'm telling. Then in case of the concrete, so whereas everybody were aware that it is the compressive strength which governs the fundamental behavior of the concrete, because when you cast any beam or any slab, so they are going to bear the superstructure load and safely transmit it into the substructure, that is onto the soil. But when it comes to the soil is in a semi-infinite media, not as an individual member. See, this is the most important thing you have to understand. The soil is a semi-infinite media. It doesn't exist in like an independent member. like a concrete or a steel. So we don't say that we will segregate the soil and thereby build our structure on that particular type of the soil, which never happens. So we consider whole earth as a soil, and thereby we lay our foundation on that particular soil. So when you apply the superstructure load onto the soil, so there are two ways of the load transfer happens. One is in vertical direction, next is in horizontal direction. That means the stresses develop both in horizontal direction as well as in vertical direction. While you may ask the same question, will that not happen in case of the concrete or steel? Just imagine yourself, will it happen in case of the concrete and steel? Any answer, logical answer?
No, sir.
No, why?
Sir, the members will be designed either to have vertical loading or longitudinal loading. That's why.
Okay, so more than that, see this concrete member, this steel member have a finite geometry. They don't have infinite geometry like a soil. If you look at the soil has an infinite geometry. Although particles are particulate, that is individual particles, but this is an infinite geometry. That's why we never say, so we say that the soil is only this particular length. We say the footing is this particular length as a definite geometry. But if you look at the concrete, the width of the column is definite, the length of the column is definite, anything, any member is a definite geometry. Similarly, steel. So therefore, there is no way the loads are getting transmitted in both the directions. So steel means only in one unidirection, concrete also unidirection stresses. But in steel, this is not unidirection. The stress development or the stress distribution is in three-dimensional. That's why we come up with sigma 1, sigma 2, sigma 3. Although we say sigma 2 and sigma 3 are both are equal, and thereby, so it is a confining pressure. Okay, so this is one thing because of these three-dimensional stresses, and in general, in the nature, if we apply the vertical and lateral stresses together on any material, it is irrespective whether it is a soil or the concrete or the steel, which obviously fails only in the shear criterion. It won't fail in compression or tensile. It won't fail in compression or tensile. So these are the small pictures for demonstration. Now the shear strength behavior is further complicated by the presence of the water, because when you apply a load, there is always a load sharing between the soil particles and the water, and this load sharing is a dynamic mechanism. It is not a static mechanism. Why? Because the soil particles, they will try to readjust themselves until there is a dense packing is possible. But if you look at the pore water or the water, when water load is coming onto the water, prima facie, everybody well aware that water cannot able to take any shear load. So therefore, since it cannot able to take any shear load, it tries to get escape or try to bear until such condition arises where it could able to burst out something. So these are the two possible phenomena on water when you apply any load. Okay, so it could able to bear until such an extent where it could burst the other media. This typically happens in case of the earthen embankments. Therefore, the presence of a water makes the shear strength more complex. This is the reason we normally determine the shear strength of the soil. So when you go to further details, you can understand in a much better way. So let me go into the very fundamental details because this comes from your solid mechanics or something. Stress is the force per unit area on a surface. As you can see, so this is surface. You can put either normal stress alone or the shear stress alone, or the combination of the normal stress and the shear stress, which results in the resultant stress. So this is called as a stress vector. This is what you read in your engineering mechanics. Okay, so all the shear strength theory got derived from the engineering mechanics only. Especially the shear strength theory is totally derived from engineering mechanics. That's why all our shear strength principles are derived by the mathematicians, not by the civil engineers. Normal stress is the component of the stress acting perpendicular to the surface, while shear stress is the component which acts parallel to the plane. Now in your solid mechanics, you have already understood. Is there possibility of the normal stress without shear stress?
Yes, sir.
Yes. And is there a possibility of the shear stress without normal stress? Got the question or not? So both are possible, but may not be in a soil or may not be in a one particular material. So this may be a specific case. So there is a possibility of the shear stress without the normal stress, and there is a possibility of the normal stress without the shear stress. I will explain all those things, but not in detail. Let's see. So this is the stress, simple understanding of the stresses. If you take any point O, so we have understood what are the principal stresses and what are the principal strains, principal stresses planes. So at any stress point, there exist three orthogonals. Suppose, for example, if you take this horizon, so we can able to draw three dimensions, x, y, and z. Two in horizontal direction perpendicular to each other, one in either depth direction or the height direction. So if it is a depth, it is minus, it is a height, it is positive. So orthogonal planes on which the shear stresses are zero, on which the shear stresses are zero. Example for a stress point O, there can be xy, and xz. These are the planes: xy plane, xz plane, then yz plane. Yz stresses will be zero. So these planes are called as a principal stress planes. Try to understand. These are the planes, not stresses. Principal stress planes. And on these planes acts stresses. Those are called as a principal stresses. The normal stresses which act on the principal stress plane are called as the principal stresses. Principal stresses. So in the z direction it is sigma 1, in the x direction sigma 3, y direction sigma 2. We can give any designation. So it doesn't matter as long as you could able to so convergent with it. The maximum of these stresses in the major principal stress is sigma 1, that is in the vertical direction, and the minimum stress is called as the minor principal stress, that is sigma 3. So you may ask a question, why sigma 1 should be maximum and why sigma 3 should be minimum. This already you understood when you dealt with your earth pressure theories. So the ratio between sigma 1 and sigma 3 is called as a what do you call this ratio?
Pressure coefficient.
Earth pressure coefficient. Okay, the ratio between that is sigma 3 by sigma 1 or sigma h by sigma v. Okay, K is called as the ratio of sigma V by sigma H. That means certain fraction of the sigma 1 is equivalent to the sigma 3. So depending upon the direction, that is vertical or horizontal, if it is moving the wall away, it is called as active earth pressure, and if it is moving the wall towards the soil, it is called as a passive earth pressure, and if it doesn't move any direction, it is called as a at rest condition. Here from here you can understand. So there is no independent mechanism of determining the sigma 3. We take sigma 3 as a part of the sigma 1. However, depending upon the direction of the stresses. The intermediate stress is termed as the intermediate principal plane. As I told you, in general in soil mechanics, not for other materials, in general in soil mechanics, if you apply any vertical stress sigma 1, there is a possibility of the development of equal value of sigma 2 and sigma 3. There can't be any difference unless otherwise this media is different, the media of this plane is different, media of this plane is different, but which is not a possibility in case of the soil mechanics. Therefore we always take sigma 2 is equivalent to the sigma 3. That's why this entirely thing is called as a confining pressure. So interested in two-dimensional stresses and more importantly the planes containing sigma 1 and sigma 3. So the difference between sigma 1 and sigma 3 is called as a deviator stress or stress difference. So this part also you understood in your shear strength theory. So this is a simple mechanism. Suppose if you take a unit length of the failure plane, this AB is a failure plane, because if you apply the vertical stress, that is sigma 1, and the sigma 3. So then there is a possibility of the development of the failure plane all along the AB. Suppose if AB is an unit length, then the length of the AC plane is 1 into cos alpha, and the length of CB plane is 1 into sin alpha. 1 into sin alpha. Okay. So Mohr so based on this one, so Mohr is one person who tried to determine the value of the normal stresses and the value of the shear stresses depending upon the horizontal stresses H and vertical stress V. A simple question is that you are asked to determine the shear strength of the soil at which the soil fails. These shear stresses are N and T, but which develop on a particular plane AB with a failure plane of alpha. So these stress developments, the failure stresses development, are highly dependent on how much you apply the vertical stress, that is V, and horizontal stress, that is H. Of course, even if you apply only V, there is a possibility of the development of the failure plane, and even if you apply H and V together, still there is a possibility of the failure plane. But if you apply H and V with equal intensity, so there may not be any failure plane. Okay, you try it. If you apply equal magnitude of H and V, what happens to the failure plane? Now once we can apply the horizontal stress in the form of a confining pressure, vertical stress in the form of a deviator stress, then what would be the values of normal stress and tangential stress, and F is the resultant of these two. So this is the equation. These equations are equivalent to the circle. Like for example, I will demonstrate like a tau. This is sigma 1 minus sigma 3 by 2 into sin 2 alpha. If you take sigma 1 minus sigma 3 by 2, this is equal to the radius of the circle. You forget about the sin 2 alpha. So this is what, if you recall the Mohr circle diagram, the vertical ordinate sigma 1 minus sigma 3 by 2 by is nothing but your shear stress, and normal stress, which is the distance from horizon to the center of the circle, that is sigma 1 plus sigma 3 by 2 plus sigma 1 minus sigma 3 by 2 into cos alpha. So depending upon the applied sigma 1 and sigma 3, you can able to determine the normal stress and the sigma stress if the failure plane is known. So plotting this circle in the T sigma space for the element gives the Mohr circle diagram. Okay, so Mohr is the one person who found out the easy way of determining the normal stresses and shear stresses. I will take a complete 1 or 2 classes on the Mohr circle, maybe after this class. So this represents the state of stress at a point at equilibrium. Okay, this sigma and tau represents the state of a stress at a point at equilibrium. At any point on the circle represents the stress, that is sigma and tau, normal and shear, on a plane inclined at an angle alpha to the horizontal plane or the minor principal stress, whatever, depending upon the case. So this is simple example. You can note it down and solve it using the previous equation. So here, when applied 20 kilonewtons of vertical stress and 40 kilonewtons of the horizontal stress, a failure plane is developed with an inclination of 30 degree with respect to horizontal. Then you are asked to determine what is the normal stress and what is the shear stress at a particular point all along this plane that caused the shear failure in a soil sample. So then what is the importance of studying this Mohr circle or the shear strength? So when we say, when do we say a foundation or a slope has failed? If the load or stress is increased until the deformations become the unacceptable range. Okay, now the validity of this statement is very crucial. Now when I say the load is increased until the deformations or the settlements are becoming unacceptable, unacceptability means we have prescribed some settlement values. Suppose if you look at the isolated footing, the allowable is 25 millimeter. If you look at the combined, then 40 millimeter, 50 millimeter. That means if the settlement exceeds this value, then the stress failure may arise. That means settlement induced stress failure, which can happen in any foundation or the slope, doesn't matter. So in this case, we are referring to the strength of the material, which is really maximum or ultimate stress of the material that can sustain. Now, there are two things normally you deal with when you are ready your shear strength and shear stress. These are the two things you have to understand: shear strength and shear stress. Shear strength means it is the resistance offered by the soil under intact condition or the field condition. Okay, shear stress means this is the load imposed on top of a soil which causes the development of the shear strength. That's why if you look at your factor of safety equation, it is nothing but shear strength upon shear stress, meaning thereby if you apply the external load on the soil mass, which should be much lesser than the shear strength of the soil, which otherwise the slope fails, or the foundation fails. So in geotechnical engineering, we are generally concerned with the shear strength of soils and rocks because the most of our problems in foundation failure results from the excessive applied stress. So if you have any question, please ask me. If you are not clear about what is the meaning of the shear strength, what is the meaning of the shear stress, please justify right now. If anybody has any question on the fundamental distinction between the shear strength and the shear stress, please get clarification. Okay. So this is a simple demonstration. You already experienced this one. Suppose if you take our triaxial element. So AB is the failure plane and sigma and T are the normal stresses. And if you try to superimpose this one on our Mohr-Coulomb failure, shear stress versus normal stress. So this is failure envelope, where C is the cohesion intercept. Point A is below the failure envelope, no failure, and point B is verge of the failure or failed. C is not possible because the soil has already failed. So then these are called as Mohr circles. So if you look at this one, so the fundamental meaning of this thing is that the normal stress on the x-axis and shear stress on the vertical axis. Now in all triaxial test, we apply the sigma 1 and we apply the sigma 3. But however, we will keep the sigma 1 constant, that is cell pressure constant, and keep on applying the deviator stress until the soil fails. So this initial circle A indicates the initial state of loading condition where we applied the sigma 3 and sigma 1. Then what we do? We keep on increasing the deviator stress until the failure plane, until the soil fails or the shear stress reaches to shear strength. This inclined line, this indicates the shear strength of a soil. While when you apply the load or increase the deviator stress in the triaxial setup, you are increasing the shear stress, and this shear strength, when it reaches the shear strength, then the soil fails. So this is interpretation of the Mohr-Coulomb. So this is sigma 1, this is triaxial element, sigma 1 the vertical stress, sigma 3 the cell confining pressure, and this is the failure plane. Theta is the angle made by the failure plane with respect to horizontal. The same thing can be converted into Mohr circle. Sigma 1, this is the sigma 1, and sigma 3, this is sigma 3. So sigma 1 and sigma 3 will become the two points of a circle, and based on sigma 1 minus sigma 3, that becomes the diameter of the circle. The difference between sigma 1 and sigma 3 is diameter of the circle, and as I told you, the sigma 1 minus sigma 3 by 2 is nothing but the radius of the circle, which is also nothing but shear strength or shear stress. The distance between C and D is sigma 1 minus sigma 3 by 2. So strength envelope, this is known, and based on applied sigma 1 and sigma 3, you can develop the Mohr circle diagram. And theta, that is the angle made by the failure plane, which is nothing but the point connecting the pole. Actually, you have to understand about the pole. I will explain about all those things. So pole point with the maximum point at which the soil fails, that is point D, the point D. So this angle is called as a angle made by the failure plane, which is nothing but theta is equal to 45 plus pi by 2, where pi is the angle of internal friction of the soil sample. So angle of internal friction of the soil sample. So one way we are relating the friction angle with the failure plane angle. That means the development of the failure plane is solely dependent on the angle, the internal friction of the soil sample. Okay. Okay. Now there is a question also. This theta angle made by the failure plane, if only depends upon the pi, then what about the shear strength of the soil? Shear strength depends on what parameters? Okay, so this is the fundamental mechanism of the resistance of shear resistance by the soil particles. So this is the mechanics that everybody well aware of, but let me recapitulate. If there is a smooth or hard surface, and when you are applying the normal stress and shear stress, that is horizontal stress, then shear stresses develops at the bottom all along the surface. So all along the surface, that is normally represented as mu. This is friction coefficient. This is the friction coefficient. So T is equals to frictional times the normal stress that is applied. The normal stress that is applied. Indirectly, the magnitude of the T indicates that this is the amount of force required to overcome the friction. That's it. There is nothing. Okay, so T indicates the amount of force required to overcome the friction. But when you talk about the friction, if you recall your engineering mechanics, you understood about the two frictions, static friction and kinematic friction. Is it true? Static friction and kinematic friction.
Yes, sir.
So can anybody able to distinguish between these two? Static friction and kinematic friction.
So static friction is the friction which is applied by the ground to counteract the forces that are applying in the lateral direction. It is not the maximum friction. While kinematic friction is the maximum friction that is applied when the object is in moving direction.
Very good. Okay, suppose if you look at this graph, the up from this point to this point, this is called as a static friction. Okay, that means the amount of the force required to just initiate the mobility. The same thing is also valid for your mobilized cohesion and mobilized angle of internal friction. Once mobility has started, you don't require that much friction again. You require slightly lesser friction because the body is in a moving condition or in a motion. So the friction which is required when it is in a motion condition, that is called as a kinematic friction, and the motion or the friction which is the force which is required to mobilize the any motion of a body, that is called as a static friction. Okay, the same thing is valid in case of the soil particle also. So the amount of the tensile force or the shear force required to mobilize the friction or the mobilize the cohesion, that is called as a mobilized cohesion or the mobilized angle of internal friction. Once that is done, then you require little lesser amount of cohesion and the friction to further continue the failure or to further continue the motion. So the resistance of the soil deformation, shear strength, is influenced strongly by the shear resistance at contact between the particle. Now here it is easy to understand. That is, a friction is developing. But if you take out this one and put it under the microscope, then you can see lot of protrusions which are offering like a saw teeth. So every teeth is offering the resistance. That resistance is called as a shear strength. Okay, But if you look at that particular angle of a teeth, that angle is equivalent to your angle of internal friction. Your angle of internal friction is nothing but the angle made by the saw teeth. Say for example, this is saw. So this is the teeth angle. Okay, say this is the surface. The angle of this one is nothing but your pi. So this is nothing but your pi, angle made by the failure plane. Okay, the same principle is valid in case of the soil also. Maybe next slide I will show you. Okay, the shear strength refers to the soil's ability to resist sliding along the internal surfaces within a soil mass. Now, if you ask what is the distinction between this schematic diagram and our soil, this is a surface area. Here the whole resistance is equal to the area. But in case of the soil, the shear resistance is summation of the resistance by the numerous soil particles. It's not an individual soil particles. It is numerous soil particles. Okay. Then the shear resistance is proportional to the normal force pushing the particles together. When you apply the shear stress alone, you can't apply the shear stress alone without applying the normal stress. But without shear stress, you can apply the normal stress. There is a possibility. But without normal stress, you can't apply not much shear strength. The reason being, just try to imagine on this body only. In absence of the normal stress, if we apply the shear stress, this will get lifted up. Instead of moving in horizontal direction, because of the body weight, that is self weight of the body, it tries to get lifted instead of the moving in horizontal direction. Okay, that is the reason we have to always apply the normal stress. But there may be possibility of even without normal stress, we can still apply the shear stress, but very limited. There is a particular case, only maybe a particular cases. Okay, so this is the fundamental mechanisms of the shear strength development. So shear strength is nothing but resistance to shearing stresses. Shear failures occurs due to the sliding and rolling. You can understand how the sliding and the rolling occurs among the soil particles. Okay, so this is called as a rolling of one particle over the other. As a result of rolling and sliding, we can achieve the densest possible state of the soil mass. Okay, when there is a sliding, the sliding is the first one, followed by the rolling over. So the sliding initially adjusts the particles to pack in such a way that the soil mass achieves the densest possible state. Once sliding is completed, then rolling takes place. Rolling means, now let us try to understand. When particles are rolled, suppose this particle is rolling over this particle. You can see this is the angle. This is the inclination between these two. That means there is a possibility of development of normal stresses between these two. Normal and shear stresses between these two. Okay, normal stress is because of the overburden pressure, and shear stresses, that is because of the friction when this particle is trying to roll over. When this is trying to roll, it makes a contact angle or contact with a particular angle. That particular angle is called as a angle of internal friction. Okay, for example, here we can see here the angle of internal friction is during the sliding, the angle of internal friction is a 90 degree. That's why the sliding is quite easy. But during the rolling, the angle is not 90 degree. It is lesser than that one. That's why it requires immense amount of overburden pressure to roll the particles one over the another. So now if you look at this one, this hypothesis is typically valid for coarse grained soils like a sands. So this is what exact phenomenon happens in case of the sand, sliding followed by the rolling. Now you may ask a question, can this phenomenon will not happen in the clayey soils? In clayey soils, rolling possibility is very minimal. There is a possibility of the sliding, but before sliding, now just try to imagine when you talk with the cohesive soils, initially they are bound over by another force that is called as a cohesion. This cohesion is a summation of the cementation effect plus the electrostatic attraction between the particles. Cementation in case of the sand grains, it may be the cementation may be 0 in case of the sand grains. Okay, so but in few soils, suppose if you collect any soil sample from the natural as it is, then you can find some amount of the cementation effect. But if you remove the soil sample, the cementation becomes 0. Okay, but obviously there exists an electrostatic attraction between the clay particles because of the repulsive forces or the attraction forces or because of the development of the diffusive double layer or negative charge. So therefore, in case of the coarse grain material, the moment we apply a load, initially sliding initiates or gets triggered, and this sliding further triggers the rolling phenomenon. So therefore, the total shear resistance in case the coarse grain soils is because of the sliding plus rolling. While in case of the cohesive soils, so we have to initially overcome the electrostatic forces. That is the force with which the clay particles are bind together. Unless you overcome this electrostatic attraction, then we cannot come on to the sliding. Once the cohesion is overcome, then you further do the sliding. In case of that's why in case of the fine grained soils, the sliding is also nothing but the residual strength. So the amount of the force required to overcome the electrostatic force, that is called as the shear strength of the soil. This shear strength could be tau max or tau peak, maximum shear strength or peak shear strength. Again, it is something like this only. Okay. Initially, when you apply the shear strength, it reaches up to the peak. Then it starts decreasing. Then it achieves the constant. So this constant is linked to the sliding. This is also called as a residual strength of the soil mass. You got it? There is no rolling of the particles in case of the fine grained soils. So this is the particle arrangement before shearing and after shearing. Okay.
Sir, what is the difference between angle of internal friction and dilatancy angle?
Angle of internal friction and dilatancy angle. So the angle of internal friction means, suppose say when the particles are rolling, if the volume decreases or volume is remained constant, the angle with which the rolling is happening under the constant volume, then that is called as a angle of internal friction. For example, during the rolling, if the volume increases, then that is called as a dilation angle. If the volume increases, then that is called as a dilated angle. Dilation means expansion. What expands? When rolling over is taking place, the volume expands, but it's not like a swelling soils or something. Very minimal. This hump is because of this dilation only. So actually this is valid for over consolidated clays. So if you look at for normally consolidated, so this is like this. In case of the normally consolidated, the moment you keep on applying the stresses, there is a constant settlement and it reaches to a peak value. That's it. But in case of the over consolidated clays, the particle is already under fully density state. So a state has to arrive where the particle should start rolling one over the another, and there is a decrease. This decrease is nothing but your dilation angle. This is nothing but your angle of internal friction. Before the peak is nothing but angle of internal friction. After the peak is your dilation angle. So this because the volume increases a bit, and thereafter sliding starts.
Okay.
Good. So anybody has any question? I hope it is clear to you now what is the shear stress, shear strength, how shear stress gets developed in coarse grained soil, fine grained soil, what is the cohesion in fine grained soil, coarse grained soil, friction angle in fine grained soil and coarse grained soil.
Sir, I have a question.
Yeah.
Sir, during the determination of the shear strength, we are considering that the failure angle is predetermined, means 45 degree plus 5/2.
Okay.
Is it, sir? The failure angle is predetermined.
No. It is not predetermined. You need to determine the failure angle. See, when you draw the Mohr circle diagram, what you do? Say, for example, the Mohr-Coulomb failure envelope. So, when you are developing the Mohr-Coulomb failure envelope, what you are doing? So,
we are taking the principal stresses value.
Yeah, principal stresses and shear stresses also, na?
Yes.
So initially what you done? You applied normal stress and you sheared the sample and determined the shear stress for a sigma 1 or sigma 3 or say 1 value. Then increased the confining pressure, then sheared the sample and determined the maximum shear strength. Again increased the confining pressure on third sample and determined the maximum confining pressure. All right. So where is this? Yeah. So this, how did you arrive at this failure envelope? You applied the normal stress, determined the shear stress. Applied the normal stress, determined the shear stress. Applied the normal stress, determined the shear stress. So when you are joined all the lines, you are saying that the slope of this one can be linked to the angle or the failure plane angle. That means the angle at which the soil particles failed, and the intercept is called as the cohesion. This is what exactly happens in the soil. But in general, you go in a reverse way now. Reverse way means I know the angle of internal friction of the soil. Then I want to know what is the shear stress and what is the normal stress at which the soil fails. Okay, you got it. Because when you design a building or when you design any foundation, what you need? You need how much load of superstructure shall I apply on a given soil.
Yes.
So from these parameters, which one is related to your superstructure load?
Normal stress.
Exactly. So your normal stress. So now if I know the pi value, I can able to determine the normal stress.
Yes, sir. From this graph.
So this normal stress can be linked to your superstructure load.
Okay.
So we go in a reverse way.
Sir, another question I have actually from the very basic, that in a previous slide, you have shown that the principal stress is acting perpendicularly, vertically actually.
Yeah.
So we are actually applying the normal stresses, na? What is the difference that normal stress and the major principal stress? Because we know that principal stress is that what the shear stress is 0. Principal plane is actually what the shear stress is 0, and you have written that the load is applied to the principal plane.
Load is applied to principal plane. You're correct.
Yes. So what is the difference? Okay.
Say for example, let us take this square only. So where is the principal planes here? Where are the
AB is the failure plane.
AB is the failure plane. Forget about the AB. Suppose if I take this simple rectangle, where are the principal planes? Simple, horizontal and vertical only, na?
Where the shear stress is equal to 0. Applying shear stress.
Applying shear stress.
Yes.
Okay. Suppose if you take this rectangle as it is, this square as it is, no normal stress, no shear stress.
Okay.
Is it true?
Yes.
Okay. Now suppose if you apply sigma 1 and sigma 3, what does that mean? How do you read it?
So that means the top plane is acts as a major principal plane and the vertical one is a minor principal plane.
Any one could be. It depends upon the amount you apply.
Okay, yeah.
Suppose if sigma 1 is higher, then this is the major principal. If sigma 3 is lower, this is minor principal.
Yes.
Okay. Now this is you are applying the normal stress on a principal plane. Okay. When you apply normal stress on a principal planes, then what is happening?
The failure plane of AB generates.
What do you call this sigma and T?
The normal stress and the shear stress.
Yeah.
At the failure.
At the failure. At the failure. That is true. Then what do you call the major principal plane and major principles? That's what you are asking. What is the major? What is the major principal plane and what is the major principal plane? Or minor principal.
Yes, sir.
I think this sigma T only. These are not. Suppose if you look at with this equation, yeah. What is this one? Sigma alpha and tau alpha.
That is the normal stress and shear stress of the soil mass, unit soil mass at any kind of failure plane.
So in your case, the maximum principal stress is the stress where the shear stress is 0.
Yes, sir.
And that has to become when theta has to become 0, na? That can happen only when theta is 0 or this alpha is 0.
Yes, sir.
If alpha is 0, there is no shear stress. Then whatever the stress is there, that becomes your principal stress.
Principal stress. Yes, sir. Okay.
You got it?
Yes, sir.
So in that case, what is the failure plane angle?
45 degree.
45 degree. That's it. So when the failure plane develops at 45 degree, there exists only the maximum normal stress. There cannot be any shear stress on that plane.
Okay. So the maximum shear stress is always acting 45 degree angle.
Exactly.
Okay, but in case of soil, I mean it is generally, but in case of soil, soil is also maximum stress is also on 45 degree, right?
No. It is always lesser than that one. 45 is possible only in case of the rocks. That's why our internal friction angle will not exceed normally more than 30. If you look at any natural soil, your friction angle will not exceed 30. Only for coarse grained sand, where the particle size is 4.75 to 2 millimeter or 1 millimeter. In those cases only the friction angle reaches about 32 to 34. And for any in general soil, it is always less than 30. That is the friction angle. And suppose if you put that 30 into 45 plus 30 by 2, so that's how you'll get a 60.
Yes, sir.
Okay. So, but if it is 45, then the shear stress becomes 0. So there is a difference between your principal stresses and this angle of internal friction. I know whether I confused you or cleared your doubt. But one thing is sure, you understood what is the principal plane or the principal stress. Principal stress is clear now.
Yes, sir.
So it is the plane of 90 degree.
Yes, sir.
Okay.
Now
it's
the
a failure
confusion is between that failure angle, I mean the 45 degree and 45 degree plus 5 by 2.
45 degree is failure plane.
Okay.
Okay. But on the 45 plane means there is no soil at all. Na? When it is 45 degree, where is that? Yeah. So when there is a 45 degree, there is no soil at all. So why there is no soil at all? When theta is 45, there is no soil at all. Because if theta has to become 45, the pi has to become 0. So when pi is 0
Purely
means,
cohesive. In the case of purely cohesive soil, it can be happens.
in case of purely cohesive soils, yeah, like a bentonite. Like a bentonite, purely cohesive soil. In those cases, it can happen. True. Okay, so is it good? I will stop it here because already 10:58.